Hello and welcome back to the channel. In this video and in the upcoming videos as well, we'll be covering a couple of examples just to revise the concepts that we already learned in the previous videos. So we'll start with a question which is very commonly asked in most of the midterms and final exams as well, in which you're basically given a sigma notation and they specify whether it's a left Riemann sum or a right Riemann sum, and based on these instructions given, you basically have to calculate the interval for which the area is bounded, which means you have to calculate the left endpoint and the right endpoint for which the area under the curve is being taken for, and you also have to calculate the number of subintervals that they are taking in order to calculate the area under the curve. So you remember, when we are approximating the area under the curve, we are basically dividing our interval into n equal subintervals, and that is basically the n they are asking for in this question. So we'll start with solving this question. So in order to solve this question, you basically have to know the prototype of how a left Riemann sum or a right Riemann sum is represented. So we'll start with the representation of a Riemann sum. So whenever you have this question, you will basically first write the prototype of a Riemann sum, which is represented by sigma k equals 1 to n fxk delta x. So this sigma notation over here is the basic representation of a Riemann sum. What makes it a left Riemann sum or a right Riemann sum, we'll cover that portion right now. So for a left Riemann sum, your xk is basically a plus k minus 1 delta x, and my delta x is b minus a divided by n. So you basically have to substitute all these values that you see on the screen in the original notation in order to make it a left Riemann sum representation. But before solving this question, we'll see where these representations come from. So you know, while approximating the area under the curve, we divide our whole interval into equal subintervals, right? And we take the width of each subinterval to be same. That is basically delta x. When we take the difference between our intervals and divide it by n in order to get equal widths or equal subintervals to approximate the area under the curve for a function. So that is delta x. What makes it a left Riemann sum or a right Riemann sum basically depends on whether you are taking the height of your first rectangle to be fa or not. Fa is basically the value of the function at the left endpoint. So if you are considering the height of your first rectangle to be fa, you're taking a left Riemann sum. But if you are not considering the height of your first rectangle formed to be fa, you are taking a right Riemann sum. I know that sounds a bit confusing right now, but we'll cover one more example in order to better visualize what a left Riemann sum or a right Riemann sum looks like. Okay, so now in order to better visualize what a left Riemann sum or a right Riemann sum looks like, I have two examples on the screen. So on the left hand side, you see that my interval is starting from 0, right? And I am considering the height of my first rectangle formed to be equal to e to the power 0, which is exactly equal to f of a, where my a is 0. So f of 0 is e to the power 0, which is 1. So now in this case, since I'm taking the height of my first rectangle to be equal to the value of the function at the left endpoint, I'm basically taking a left Riemann sum. But on the other hand, in this example, I'm not taking the height of my first rectangle to be equal to the value of the function at the left endpoint. So this is a right Riemann sum. Please note that these definitions are for simplicity, but the actual right hand Riemann sum is when you're taking the height of your last rectangle to be equal to the value of the function at the right endpoint. So if I have to summarize left Riemann sum and right Riemann sum, if you're taking the height of your first rectangle to be equal to the value of the function at the left endpoint, you're taking a left Riemann sum. But if you're taking the height of your last rectangle to be equal to the value of the function at the right endpoint, you are taking a right Riemann sum. So now we have covered left Riemann sum and right Riemann sum in detail and how we got these sigma notations. So this xk is basically the height of the consecutive rectangles that you're taking. And you see one more thing, since this is a left Riemann representation and my k is starting from 1, if I take my x1, I'll get this portion equal to 0. So the height of my first rectangle will be equal to a. That is why this representation is for a left Riemann sum. But if I have to change this representation into a right hand Riemann sum, it would look like xk equals a plus k delta x, because if I take k delta x, my x1 would be a plus delta x, which is not equal to a. So in this case, I'm not taking the height of my first rectangle to be equal to the value of the function at a. So this is basically the difference between the sigma notations of right hand Riemann sum and a left hand Riemann sum. If it's given in the question that it's a left Riemann sum, you'll use this sigma notation, but if you're given that it's a right hand Riemann sum, these two notations will remain the same, but this notation will be changed to this one. So this is the important fact that you have to take into consideration, that your sigma notations will change based on the left hand sum or the right hand sum you are taking. So now we'll move forward and solve this question. I'll write all these notations that are important for this question and move on to the next page. Okay, so I've written all the important formulas that we need in order to solve this question, and I'll start with comparing my notation of Riemann sum to the sigma notation they have given us in this question. So I'll write the sigma notation which they have given us, which is sigma k varies from 1 to 4 f of 1 plus k times 1. So now if I compare both of these sigma notations, I see that easily my n is equal to 4 by comparison, my xk is equal to 1 plus k, and my delta x is equal to 1. So I have all these values in place, and now I'll solve for a and b, because I've got my n and the only values that are remaining are a and b. So now based on these given values, I'll solve for a and b. And I know since my delta x is equal to 1 and it's also equal to b minus a upon n, where my n is 4, so my b minus a becomes n times 1, which is 4, because my n is 4. So I got my b minus a value to be 4, and since this is an equation with two unknown variables, I just have to find one more equation in order to solve for a and b, which I'll easily get by relating xk to the already given expression that I have. So my xk, which is 1 plus k, that is given in this question, and the original formula is a plus k minus 1 delta x. I'll expand this expression again. So it becomes 1 plus k, a plus k minus 1, where my delta x is b minus a upon n, and I know the value of my delta x as well. So the value of my delta x is 1. So 1 plus k equals a plus k minus 1, because this expression is equal to 1, right? So now you just have to solve for a. 1 plus k equals a plus k minus 1, and k gets cancelled out. So you have a equals 2, and since a is equal to 2, your b minus a is equal to 4. So that gives me b equal to 6. And my question is now solved. I have a, I have b, and I have n as well. So this is basically one of the easiest ways on how you can solve these type of questions. You basically have to know the prototype of how a left Riemann sum or a right Riemann sum looks like, and you just have to compare those sigma notations in order to get to the final answer. So that was it for today's video. I hope you found it interesting, but if you still didn't get the left hand Riemann sum and the right hand Riemann sum, feel free to comment down in this video and I'll make a separate video on them as well. Please follow the channel in order to get notified about the other videos that I'll be uploading, and thank you so much for watching. Stay tuned. Bye.